Hello everyone, welcome to our next video. This is for lesson 18, Graphs of Rational Functions Part 2. In lesson 17, we learned how to identify a vertical asymptote, so now let's learn how to identify horizontal asymptotes. So if you remember, the definition of an asymptote was essentially a line that a function can't ever cross. It tends to jump over it sometimes. But generally, they're lines that are created from the functions not having outputs at that particular input. So we'll go over that a little bit and a bit for a review before we move on. So our first warm-up is just that, just kind of remind ourselves on the idea of a vertical asymptote. So here's three functions, k, m, and w, and can we match them to the function? C is down below, or sorry, B is down below, and by B I meant G. Okay, so we have A, we have C, and we have G. So let's try to match them up. Now, remember that the definition of a vertical asymptote had to do with figuring out where the function no longer has value. And that happens when the denominator is equal to 0. So for vertical asymptote, so just a quick reminder of ourselves here, vertical asymptote, denominator equals 0, because we can't divide by 0. So let's take a look. For the first function, right? So what value of x is going to make this equal to 0? Well, if x is just 0 by itself, then this will no longer have a value because we can't calculate 12 divided by 0. Likewise, for this function, we can't have x being negative 2 because then we'd make that denominator equal to 0. And over here, we can't have x being positive 2. Now, the fact that there's a negative sign here does not matter. All that negative sign does is actually flip the function around. But still, regardless of whether that's negative or positive, you divide by 0 and it's not going to happen. Okay, so which function matches with which? So graph A has a dotted line at negative 2, so clearly this must be m of x. Graph C has a dotted line at positive 2, clearly that's w of x. And therefore this one down here, graph of G, dotted lines at 0, and so that one is going to be k of x. So these are pretty easy to tell. Now remember, we have a tool if we have functions with the same vertical asymptote and we need to know which is which. In that situation, we'll have to use other information such as test points or anything else about the function that we know. So whenever you're not sure, you can always just pick a number that's not one of these and plug it in for x. So maybe 1. Plug it in for x and essentially see if you get either a positive or a negative, and that will help you decide which function is which. Okay, but let's move on to dealing with other kinds of asymptotes. So example number 1. Let's say that we wish to publish a book. Now, we publish a book, and as we publish things, certainly publishing books costs money, right? So let's say we want to print, a lot of copies of a book. Now, if I print just a few copies of a book, certainly, I'm going to pay quite a bit for those copies. However, the more that I purchase is with many things, right? Whenever you buy more things, you tend to pay less for each individual thing to a point. So that happens at the grocery store, like when you buy bigger containers, you tend to pay less per unit. That might happen with something like with cases of soda, let's say. A 12 pack of soda may run you, say, $7, but then a 24 pack will only cost you $12 because it costs you less per can when you buy more of it. So here's a graph that does exactly that. Let's say we're purchasing a number of copies of a book, so anywhere from 0 all the way to 500. And on the y-axis, here's my cost per book. So it could cost, almost free, all the way up to $20 per book. Now, here is a function. Now, this particular function, let's say that this is a function that models the amount of money that we spend to make books, right? So let's see where this function might come from. So let's say that perhaps you are paying $4 per book, right? Oops, as I accidentally hit my eraser there. So let's say we're publishing $4 per book, plus say 120 as a fee, like maybe some kind of service charge, right? But then we are going to divide by the number of books, and that's going to create an average per book. We add up what we have and divide by how many we have. So this is basically a calculation of average. And this is how your average changes over time. So tell me about this graph. What is the approximate cost per book when 50 books are printed? All right, well, that's as easy as looking at the function, right? Now I can look at the function. Now I could plug it in, right? I mean, I could plug 50 into this function. I could do that too. Or I could use the graph to estimate it. Looks like it's $6.50. So if I buy 50 books, I'm going to pay about $6.50 each. Now, what if I buy 100 books? If I buy 100 books, this number looks like it's going to be more like, I don't know, maybe $5.20. So maybe we'll say that this point is $5.20 per book. So the more books you buy, the less each one is going to cost. All right, what are other questions I can answer here? All right, so enough questions on that page. So I want you to think about what's happening as you go through and you print 300, 400, 500. What seems to be happening other than it's going down, right? I want you to think about maybe is there some kind of stopping point that's happening? What's going to happen if I keep buying more and more and more and more books? Okay, the author plans to charge $8 per book. About how many should be printed to make a profit? Okay, let's go back to our graph and let's look at $8 per book, right? So we want to charge $8 per book. Okay, so if I want to charge $8 per book, right? Like this. So here's my 8 line. Now, I want to turn a profit, right? I don't want to sell these books for a loss. So if the books cost me $10 each, that's no good, right? So how many books must I need to buy so that I can be able to sell them at $8 a piece? So when I look at this, I see that, at this point here, this is where it drops below $8. So when I look at this, it looks like what, maybe 30, 35? So maybe about 30 to 35 books. Now, could I solve this as an equation? I suppose I could. So I could say 35 equals 120 plus 4x over x. Okay? Now that would be a fairly tough equation to solve. No, probably not. Oh, actually not 35. I'm sorry, not 35. That should be 8. So 8 equals 120 plus 4x over x. So I could solve that, and I'm going to get probably in the neighborhood of 30 books. Actually, in this particular case, I'm looking at this and it'll be exactly 30 books. But here's the problem. I want to make a profit, right? If I buy 30 books, they're going to cost me exactly $8 each. What if I sell them all? I don't really make a profit. I just make my money back. So actually, the reality is this needs to be greater than. So X has to be greater than 30 books. And as long as I'm greater than 30 books, and assuming I sell them all, then I'll make a profit. So I should quantify this here, if we sell them all. Okay. What is the value when X is a half? Okay, well, let's try it. So C of 1/2 equals 120 plus 4 times a half over 1/2. All right, now I might need a calculator for this. 120 plus 2, half of 4 is 2, over 0.5. Now, dividing by 0.5 is the same as multiplying by 2. And so what I have here is actually, and you could do this in a calculator, you get 244. It would cost me $244 per book. But now, wait a second. First off, that's a lot. Second off, does this even make sense? Because what happens if X is a half? That's half a book. Can we really sell half a book? Half a book? Guess not. Okay, next question. What does the end behavior of the function say about the context? As X gets larger and larger, what happens to the average cost? Okay. Well, let's really go back, and this is the question I was kind of prepping you for earlier. If X gets bigger and bigger and I buy more and more and more books, what's going to happen? Looks like it's heading towards the number 4. Now, here's my question. We know that these books, they're going to get cheaper and cheaper and cheaper. So will it eventually reach 0? And it turns out, let's look at the function for some advice here. You're charging $4 a book plus 120 fee. Wait a second. You're multiplying the number of books by 4. So you're guaranteed to have to pay at least $4 a book. Plus, there's this service charge of $120. So I'm always paying $4 per book. But the more books I buy, this service charge kind of doesn't matter. Like if I buy, say, 1,000,000 books, what would 1,000,000 books cost? 1,000,000 books would cost me $4 million plus 120. And at that point, the 120 is almost meaningless, right? And I could divide by that. So you know what? Just out of curiosity, let's open up a calculator. Okay. And although it's not going to show up here because I have it set to window presentation, but let's go ahead and divide. So let's do 4 million plus 120. So it's 4,120,000, and we're going to divide by 1 million. And the answer you're going to get is 4.00012. So as you can imagine, when you look at this function, what's happening is this function here, as it goes down, it's never actually going to cross 4. And the reason is because we already know that we are paying a base cost of $4 per book. But it gets close. This is a horizontal asymptote. So here's what we can say about it. So you might remember some of the notation that we used earlier when we did this. So as x approaches infinity, in other words, as x gets larger and larger, y approaches 4. Now, so we're not using infinity anymore because the function isn't pointing straight up and pointing straight down. Now it's actually pointing more in a different direction to the side. And so now what we're realizing is this particular function will never reach 4. It'll come really close. As x gets bigger and bigger and bigger, the value of y is settling towards the number 4. Now, in this particular case, it's never going to jump over this line. In this case, there won't be any values for which, no matter how far it goes, there will never be any values that go on the other side of 4. So that's important to realize here. So as x and x gets larger, so let's write that again here. As x approaches infinity, y approaches 4. And again, where did that 4 appear? That 4 appeared here in the original function when we looked at the slope, like how much we were being charged per book. Interesting. So this is what we call a horizontal asymptote. The line y equals c, which is a horizontal line, it's an asymptote if the outputs of the function get closer and closer to c as the inputs get larger and larger in some direction. So this means that the graph gets closer and closer and closer to the line and never actually crosses it. So it's this situation here. So now let's try matching some of these graphs up. Now here, armed with just a definition, we might need to see what other information that we can use in order to try to piece these together. But again, I want you to keep in mind a couple things. The biggest important piece to determining horizontal asymptotes is what's going to happen with big numbers. So for all of these functions, right, what we're intending to do is to try to figure out what happens when x gets really big, either positive or negative. And so what I'm going to do in this situation, now you can think of a big number, but what I'm going to do in most of these situations, I'm just going to say x equals big. This is kind of the way I like to do it. X is big. Now, how big is big? Big is as big as you want it to be. You could say huge, or you could give it like a billion or a trillion or something, right? But the actual value doesn't matter. We want to know what's going to happen when x is really big. So let's see how that applies to some of these graphs. So here's the thing with these graphs. We have an A, B, C, and a D, okay? Each one of these graphs matches 2 of these functions. Ooh, interesting. So let's see which is which. Because if we can match up an A, B, C, D, E, F, G, H, we can then get a chance to see, different representations of the same function. Okay, so I think the most important piece is when you recognize a horizontal asymptote, you want to recognize what's going to happen, as I said, when x is big. And so what I'm going to do is I'm going to take each function in turn, and I'm just going to write it, instead of x, I'm going to write big, and I'm going to think about what might happen. So for A equals 4 over big minus 1. Okay, well, how does that help? What is 4 divided by a really big number? Okay, let's go back to in class, I used the birthday cake example. So I said that when you cut something into a larger number of pieces, what's going to happen to each piece? They're going to get small. So let's say you have a birthday party and there's a birthday cake, and there is a lot of people at the party. You have this one cake, it's delicious cake, but there's a ton of people at the party, like a lot of people. But you have just this one cake. So everybody is only going to get like a crumb, basically, right? So imagine like a basically infinite amount of people. What's going to happen here? This, right? This 4 over big is going to get replaced with 0. 4 divided by big is essentially 0. In fact, it's so close to 0 that we might as well just say it's 0. And so what's the value? -1. That is the horizontal asymptote. So when we think about x, we want to think about what x is doing when it's really big. And it actually doesn't even matter if it's positive or negative. We don't care if like the actual sign, because 0 or -0, it's still just 0. So when we can just say big, and sign really in that case doesn't matter. So the issue here is I'm going to put in -1, okay? So this function has a horizontal asymptote at -1. All right, which one is that? Well, hey, that looks like that's D, right? Okay, so function A goes here. All right. So that's kind of how you're going to help figure out some of these horizontal asymptotes, is by thinking about big. Now, like maybe pardon the pun here, but to look at the big picture. Okay, that was cheesy. I'm sorry. It's late. Whatever. So, but yeah, if that works, look at the big picture. So let's look at the next one. 1 over x minus 4. Okay, same numbers but reversed, right? But does it really matter? What's going to happen if I do 1 over big? I mean, it's probably roughly the same thing. Any number divided by big, I mean, it's just going to be essentially 0, right? This part's just going to be 0. 1 divided by big is basically nothing. So this one has a horizontal asymptote at -4. That must be this function here. That's the only one with an asymptote at -4. Okay? And so let's continue kind of that same process. Okay. What about C? Ooh. Okay. Actually, let's skip those for now. Let's go down to G and H. Okay. Because G and H kind of do the same thing, right? You have 4 over x, 1 over x, but again, +1, right? So again, if x is big, what's going to happen? That's going to go away, and you're left with 1. Here, if x is big, that's going to go away. You're left with 4. So clearly, it looks like this one is going to be G, and this one's going to be H. Okay. All right. So in that particular case, all's well and good. Okay. But let's see what happens in some of these other cases. C, D, E, and F. Okay? All right. So for that, let's erase some of the stuff over here on the side. Okay? And so there's a couple ways that you can look at this, all right? So I'm going to show you two ways of doing this. The first way is to actually just divide. So if you look at C, right? Let's look at C for instance, okay? You have 1 plus 4x over 4, similar function to the one we did before, right? Okay, well, 1 plus 4x over 4, well, what's going to happen, or not 4, it's divided by x, I'm sorry. So let's change that. Okay, so it's divided by x. Okay, well, let's see. Maybe I could just divide these by x, and what I end up with is 1 over x plus 4. Hey, that's the same thing as h, isn't it? So it looks like c and h were the same function. Now, can you see where that 4 appears here? And again, how if you think about the book function that we had before, because x is just constantly being multiplied by 4, no matter what, you're always going to have 4 times some huge number. So it makes sense for the asymptote to be at 4. Oops, I made a couple of stray marks there. It's the way my pen works. Okay, so you're always going to have that. So let's look at some of these other ones, right? Well, let's kind of do the same thing. So let's look at D. X plus 4 over x. Ooh. Well, let's think about this. Let's think about this in two ways. So here, I could just divide by x, right? Okay, what's x divided by x? Well, 1, right? So I could say that this is 1 plus 4 over x. Okay, well, guess what? That has an asymptote at 1. So that one, D. So we can then do that for some of the other ones. So like same thing here. I would get for E, I would get 1 over x, and then 4x divided by x, negative 4 divided by negative 4x divided by x is just negative 4. So that one's going to have an intercept at negative 4. Same thing with this one. I'm going to get 4 over x, and then negative x divided by x, negative 1. And that's going to have an asymptote at negative 1. And that's going to match here. Now, here's another way you can kind of look at it. So let's erase some of this over here. And let's again think about the idea, the big idea, right? So let's look at D, for instance, okay? What happens if I take x, and like I did before, I replace it with big? I end up with big plus 4 divided by big. And now our question is, what exactly is that? Well, I mean, I could do what I did before and cancel them, right? But what's big divided by big? Well, any number divided by itself is 1, right? So big divided by big is about 1. Well, here's the thing. If I take some really big number, like big, like billions, trillions even, and I add 4 to it, is it really going to change that value all that much? No, not really, right? Because, I mean, a million plus 4 is still about a million. So this is approximately equal to big divided by big. Because adding 4 in this particular situation doesn't really do much. It does a little bit, but not enough to really notice. And what's big divided by big? 1. So it has an asymptote at 1 because the value is going to be about 1. And the bigger big is, the closer to 1 that's really going to be. And that's why, another reason why you get a horizontal asymptote at 1. So our concern here is what's happening in the long run. All right. So now that we've seen this though, which ones were easier to show the horizontal asymptotes? It looks like it was the A, B, and the G and the H, right? Because they were very clear to us. C, D, E, and F, we did see it. As long as we divided by X, we were still able to see it. However, when you think about the idea of just using a big number, it becomes, I guess, maybe a little bit harder to see that. And if functions get more complicated, you can see that it's kind of hard. But the idea is when we physically did that division, that asymptote actually kind of really showed up to us. And that's really important. So the functions where there is a separate constant term. Okay? So the lovely part about this is basically this happens when we divide. And another way to think about it is when we are actually able to divide this function out, that piece that's left over, that becomes your horizontal asymptote. And that's actually a pretty powerful thing to happen. So let's see how that applies in a few different situations. Okay. Um, Ultimately, it leads us to the following definition. The horizontal asymptote of a rational function can be determined by looking at the degrees of the numerator and denominator. So here's the thing. One of the things that came up, especially when looking at these functions, C, D, E, and F, because unfortunately, even though these ones were harder to see, these are the ones that you're going to see most often when it's written in a fraction form. Notice that all of these have the same degree. X, 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 X. They all have the same degree in the numerator and the denominator, right? So when I said that X is just big, what ends up happening is I essentially get a big number divided by a big number. And as we discovered before down here, some big number divided by some big number is essentially about 1, give or take, right? So that's going to become important to help us define these. Okay, so here are some rules on horizontal asymptote. If the degree of the numerator is less than the degree of the denominator, you have a horizontal asymptote at 0. Now, why is that? So that's rule number 1. That matches with F here. Okay, F has a degree of 3 and a degree of 4 in the denominator. Okay, so why does that produce an asymptote at 0? Well, let's think about what happens when x is big, right? If x is big, what's x squared going to be? Big squared, right? It's going to be huge. And then each power is just going to get even more huge based on that. So a good way to think about it is you look at these functions, right? And you have 3 times some very, very big number, x to the third. Some big number to the third power is going to be really, really big, right? And then x here is going to be big, but not as big as x to the third. So x to the third is going to drown these other terms out, and the plus 8 is going to do almost nothing. So what you end up with here is the situation where you have basically something that is pretty big divided by something that's even bigger. Divided by something even bigger. So let's think about that. Now, suppose you have a cake, right? And again, if we think about the birthday cake, but let's say that birthday cake is absolutely massive. It is a massive cake. Let's say it's a cake like the size of Texas, right? Um, but the amount of people that show up to this birthday party is just mind-bogglingly huge. That and so what's going to happen is eventually you will reach a point that even though that cake is big, very, very, very big, you have so many people that you still end up with a situation that everybody gets almost no cake. So you are dividing by a much, much, much larger number. Okay. So another way to kind of look at it, to maybe kind of make this also um, kind of stretchy here, kind of stretch the point out a little bit here. Remember, x to the third, x to the fourth, these are big, big terms, right? Um, but which one is bigger than all of them? X to the fourth, right? So this is small, this is small, this is small compared to that, right? So what you then have is basically these three numbers can essentially be ignored. And then what you have is you essentially have um, 3x to the third over 2x to the fourth. I can cancel out 3x's, and what I'm left with is 3 over 2x. And if I try to put big into this, I get 3 over 2 times big, and we already discussed here. Now it makes a little bit more sense. That's going to be 0 because 3 divided by a huge number is just 0. So basically, what comes out of all of that is the degree of the numerator. If it's less and the denominator is the bigger one, you automatically have a horizontal asymptote at 0. Okay, now the next one, degree of numerator is greater than the degree of the denominator. Okay, if the numerator is bigger, okay, degree of numerator is greater than degree of denominator by 1. No horizontal asymptote. Ooh, okay. So that's an interesting one because as long as bigger, what's going to happen is that function is just going to go up and up and up and up forever. Okay. Now I don't have an example of that one exactly handy, but this is the case if you had, say, like x to the third minus 5 over x squared. This particular function will not have a horizontal asymptote, and the reason for it is because this number is just going to get big, and it's just the numerator is just going to get bigger and bigger and bigger, and it's never going to settle anywhere. Okay, you're just going to have big numbers over something not so big, and it's just going to keep going up and up and up and up forever. So keep that in mind. So degree of numerator is greater, no horizontal asymptote. Degree of numerator is less, 0. Now if they're equal, the horizontal asymptote is at the ratio of the leading coefficients. And that comes out of what we did before. So in this particular situation here, the degree of the numerator and denominator are exactly the same. They both have an x, so they're both the degree of 1. Now, what happens if you try to put a big number in for x, right? You get 5 times big plus 1 over 3 minus big. So what's going to happen? 5 times big plus 1 is still going to be big, right? It's going to be a very big number. The plus 1 doesn't really basically ever do anything. So it's almost like we can ignore it. And then down here, this big number, okay, is if we take 3 and we subtract a big number from it, what's going to happen? You're still going to have a big number, but it's going to be negative. It's just going to be on the other side of the number line. We can still safely ignore the 3 in this situation, but what we end up with is just a negative big number. Now what'll happen? Big divided by big cancels out, and you're left with 5 over negative 1, or negative 5. So this one will have a horizontal asymptote at negative 5. And that's because the degrees are equal here. Degree of numerator is equal. We find a ratio. Okay. So that's your main rule for horizontal asymptotes. Now, there are some other fringe rules that can happen, like when the degree of the numerator is greater by 2 and things like that, but we're not really going to worry about that right now. We'll get to that at some other point. Okay, so let's identify. For the functions below, identify the horizontal asymptote and explain, right? Okay, so first things first for all of these functions, the very first thing you do is you find the degrees. Find the degree of the top, find the degree of the bottom, okay? So, in this particular situation, degree, looks like we have a 3, and on the bottom, we also have a 3, highest exponents for degree, okay? Because they're the same, we're going to use the ratio of the leading coefficients, and so the horizontal asymptote is going to be at 6 over 2, which is 3. Now, that's a coincidence that it's the same as the degree. That doesn't always happen. But if you chose a very, very large number for x, you would get an answer of approximately 3. Simply because x to the third is going to drown out these terms over here, and they're going to kind of go away. All right, next one. X squared minus 4x plus 1 over x plus 2. Here in this case, degree is bigger. We have a degree of 2 on the top. We have a degree of 1 on the bottom. So in this particular case, what will happen? There is no horizontal asymptote. And for this one here, degree of the denominator is bigger. You have a 2 over a 3. Just keep in mind the terms may not always be in the right order, so don't always just look at the first terms. These ones are good, but sometimes you might see ones where they're not in the right order. Here you're going to have a horizontal asymptote at 0 because the denominator is just going to get so big that the value essentially becomes 0. And if you don't believe me, go ahead and graph it and see what happens. All right. So, as long as you can follow the rule, that's really all there is about finding horizontal asymptotes. But it takes a bit to kind of get to this step, to kind of understand why that rule happens using really big numbers. But once you understand the idea of what happens at big numbers, it becomes easy to kind of just apply the rule. Okay, now let's go further, and now let's put it all together. And let's find both horizontal and vertical asymptotes. Yay! All right. So now that we know about horizontal asymptotes, again, let's remind ourselves, how about verticals? Vertical asymptotes exist when denominator equals 0. Okay. So let's start horizontal and vertical, okay? So in this particular case, again, let's look at degree. Denominator is bigger, right? 2 versus 1, so y equals 0. This first graph will have a horizontal asymptote at y equals 0. Now, what about vertical asymptotes? Vertical asymptotes occur when the denominator is equal to 0, which means we need to set this equal to 0 and solve it. Okay, now a function like this, how do we solve a function of this type? Ooh, it's a quadratic. It's got x squared. Hey, could I quadratic formula? Ooh, could I factor? let's try factoring it, because remember, that's our first line when dealing with these sorts of trinomials. See if it can be broken down without having to do anything fancy. X and x. Can I find two numbers that add to -5, multiply to -6? -6 plus 1. And so I'm going to have vertical asymptotes at x equals 6 and x equals -1. So vertical asymptotes, it's just like finding x-intercepts, but we're just finding them in the denominator. And because we're looking to make sure that we want to remark when this function has a 0 in the denominator. All right. And so that's really how we can put it all together. How about this function? Horizontal asymptote. Same degree, x squared. So we divide 2 divided by 1. We have a horizontal asymptote at y equals 2. Now, denominators are trinomial. Let's try factoring it. And so we have x and x. Well, let's see. -8. So 4 times 2. So -4. No, plus 4 minus 2, because they have to add to a positive 2. And so my vertical asymptotes are x equals -4 and x equals +2. Fantastic. And finally, how about this one? Top and bottom. Well, the top one, let's see, bigger degree on the top, x squared versus x. So no horizontal asymptote. And then here we only have a single vertical asymptote, and that's at -2. +2, I mean. +2. And that's really all there is to it. So that's allows us to kind of tell what are some important characteristics of these graphs. Okay, so that's putting all the rules together. So finding the end behavior reveals horizontal asymptotes. And so we can read the definition below. So in this particular one last example here, degrees are the same. So because the degrees are the same, we can think about it as 2 divided by 3. 2x squared divided by 3x squared. It's just 2/3. The 1 is going to get drowned out by all the other big, big, big values. Okay, that's kind of how it works. All right, folks, and there's your. You can read the. You can always pause and read the description if you like. All right, folks, we are done with that. Have yourselves a lovely evening. Work on the lesson 18 problems now. Okay, take care.